The problem asks for the area of the red semicircle inscribed within this right-angled triangle. We are given two lengths. The vertical side is 12 and the outer segment on the hypotenuse is 8. First, let's label the vertices as A, B, and C, and the point of tangency on the hypotenuse as D. Applying this to point A, the two tangent segments are AC and AD. Therefore, their lengths must be equal. Since the length of AC is given as 12, the length of segment AD must also be 12. Consequently, the full length of the hypotenuse AB is the sum of AD and DB, which is 12 plus 8, yielding 20. Let's formalize the solution. Step 1 is to determine the length of the hypotenuse using the two-tangent theorem. From the two-tangent theorem, tangent segments from the external point A are equal. Thus, segment AC equals segment AD, which means AD is 12. The total length of the hypotenuse, AB, is the sum of segment AD and DB. This is 12 plus 8, which equals 20. For step 2, we will find the length of the base, BC, by applying the Pythagorean theorem to the right triangle ABC. The theorem states that the square of A plus the square of B equals the square of C. For this triangle, this translates to AC squared plus BC squared equals AB squared. Substituting the known lengths, we have 12 squared plus BC squared equals 20 squared. This gives us 144 plus BC squared equals 400. Solving for BC, we subtract 144 from 400 to get 256. The square root of 256 is 16. Therefore, BC equals 16. To find the radius, our third step is to establish a similarity between the large triangle, ABC, and a smaller triangle, ODB, where O is the center of the semicircle. We can prove this using the angle-angle similarity criterion, which requires showing that two corresponding angles in the triangles are equal. First, both triangles share a common angle at vertex B. Second, both triangles contain a right angle. Triangle ABC is right-angled at C by definition. Triangle ODB is right-angled at D because the radius of a circle is always perpendicular to the tangent line at the point of tangency. Since two corresponding angles are equal, we have proven by angle-angle similarity that triangle ABC is similar to triangle ODB. For step 4, we use the properties of these similar triangles. Specifically, the ratio of their corresponding sides must be equal. This means the ratio of side AC to BC in the large triangle is equal to the ratio of the corresponding sides, OD to DB, in the smaller triangle. Let r be the radius, which is the length of OD. Substituting the known values, our proportion becomes 12 over 16 equals r over 8. To solve for r, we multiply both sides by 8. This gives r equals 8 times the fraction 12 over 16, which simplifies to 6. For the final step, we can now calculate the area of the semicircle using its radius. The area of a semicircle is given by the formula 1/2 times pi times the radius squared. We substitute our calculated radius of 6. 6 squared is 36. Half of 36 is 18. Therefore, the area of the semicircle is 18 pi.